All right, we're looking at section 3.10, which is on linear approximations and differentials. First up, let's look at the main idea behind both of these things. Suppose that you had no calculator available and you needed to come up with an approximation of these. Now, each one of these things, what they have in common is each one of them is asking us to evaluate a function at some number, but somewhere near to that number, there's another number that would be a lot easier to plug in. For example, square root of 50, it'd be a lot easier to find square root of 49. So we can use this as kind of an estimate and say square root of 50 is going to be a little bit bigger than 7. Same thing here, sine of 32 degrees. It'd be a lot easier to take sine of 30 and get 1/2. And then know that this is a little bit bigger than a half. This right here is going to be slightly less than 4 squared, so this is going to be a little under 16. And log of 105, well, log of 100 is 2. So this is going to be a little bit bigger than 2. The idea is that linear approximations and differentials, they'll let us use derivatives to get an accurate estimate of these things. So what I want to do is I want to sort of develop the idea by concentrating on square root of 50. And I want to build up to this formula here. But let's talk about this a little bit first. So the idea is you're given some function f of x, and you're asked to approximate the value of f of x for some x value that happens to be near a nice value you can plug in. The nice value is what we're going to call a. So up here, the a's that we would use for each of these would be, in this case, 49. This one 30 degrees, this one 4, and this one 100. So what I want to do is just sort of work through this, and we'll build up this formula here. And I want to do this by concentrating on what I think is the simplest of these, which is square root of 50. All right, so let's do this. The function that I'm interested in here for this one is f of x is square root of x. And our a here is 49. That's the nice nearby number. And I'm going to go ahead and take the derivative. F prime of x is 1 over 2 root x. So let's graph this function. All right, we know what square root looks like. It's a half parabola. Looks like that. And somewhere over here is 49, our a. And over here is 50, the number we're trying to evaluate it at. Now I know I have this drawn out of scale, but that doesn't matter. Let's come up here and label some points. This point here is 49, 7. And this point over here is 50 square root of 50. And that's the number that we're going to try to come up with an approximation to. So let's see. What I'm going to do is draw in a tangent line here. I'll do that in purple, I think. Let's see. So here is, I think I'm better off just drawing this by hand instead of trying to get the iPad to do the perfect line for me. Actually, I'm going to cheat. I'm going to make it do 2 perfect lines for me. All right, so here's my tangent line. It's not perfect, but it's close enough. Gets the point across. We got the tangent line there. What we want to do is we're going to pick this point here on the tangent line, and we're going to use this to approximate. Well, its x-coordinate is 50. Its y-coordinate is going to be approximately 50. Or approximately the square root of 50, rather. Its y-coordinate. So we want to figure out what that is. Now, why is it approximate? Well, it's going to be a little bit bigger than square root of 50 because the y-coordinate of this point, of course, is bigger than the y-coordinate of the one below it. but it's going to give us something fairly close. All right, so what's the slope of this line? Well, let's see, this line, the slope is going to be f prime of 49. And that's going to be 1 over 2 root 49, which is 1 over 14. All right. So there are two things we could do from here. Well, one of them is, notice this, we've got a point here on the line, and we've got its slope. So the equation of the line, I'm going to call this line L of x. And that's short for linearization, because this is a linear approximation to the square root curve. Now the square root curve is close to the line as long as we stay close to this point 49, 7. So let's work out the equation for this L of x. L of x is, let's see, so let's don't call it L of x just yet. For this line, we've got y minus y1 is the slope times x minus x1, which is 49. So we get y equals 1/14 x minus 49 plus 7. And that's what we're going to call L of x. That's my linearization of this function at 7. Now, if you compare that to this down here, the linearization of f of x near a is this. Notice you got f of a, well, that's 7, plus f prime of a, that's what we got here for this 1 over 14, times x minus a. So what we've built up here is this this tangent line, and it's an approximation to the actual curve. So if I wanted to figure out what 50 is, I just do L of 50. Now let me change to purple for that. You do L of 50 is equal to 1/14 times 50 minus 49 plus 7. And so this winds up being 7 plus 1 over 14. So this tells us this is approximately square root of 50. Now, let me grab my calculator, and I want to do both of these. I'm going to do 7 plus 1 over 14, and I'm going to do square root of 50 on the same screen. And let's see that. Whoops, that's the wrong thing. Cam only. All right, if you look at that, 7 plus 1/14 gives you that, and square root of 50 gives you that. And they're the same down to 3 decimal places. I guess we could come up with percent error if we wanted to, but I don't want to do that. Anyway, it's a pretty good approximation. Now the idea here, this is the linearization, or the linear approximation. Another thing we could do, if we wanted, is you could look through here and find what is the difference here between the y-coordinate of this point and the y-coordinate of that point. And if you do that, what you get there is this is 1/14. Because this is, if you look at this and think of it as rise over run, we're running 1 and we're rising 1 over 14. So another way you could think of this is this has a y-coordinate of 7, and you add 1/14 onto it. That'll give you the 7 plus 1/14. And this is really more of the idea behind a differential than the linearization. So anyway, that's where this stuff comes from. The thing that I want to really do here is use this formula down here. This formula for the approximation of f of x using a linear approximation. We'll look at that in the next video.